Hello students, I am Onov Mondol, lecturer of Mechanical Engineering, Department of Camellia Institute of Technology and Management. So let's start today's solid mechanics class. So in our previous class, we discussed about the plane state of stress, and we see that maximum shear stress is, I write. So maximum shear stress is tau max, that is equals to uh, half of sigma 1 minus sigma 2. That is sigma 1, we know that sigma x plus sigma y by 2 plus root over sigma x minus sigma y by 2 whole square plus tau xy whole square, and then minus sigma x minus plus sigma y by 2, and this is minus minus plus root over sigma x minus sigma y by 2 whole square plus tau xy square whole to the power half, and that is that root over tau max is equals to sigma x minus sigma y by 2 whole square plus tau xy square. So today we'll move to another topic, that is differential equations of equilibrium. Differential equations of equilibrium. Okay, now we know that in general the state of stress in a body varies from point to point. So we have to determine the state of stress at every point or at every desired point in a body. So we analyze it by dealing with the conditions to be satisfied by the stress components when they vary from point to point. These conditions will be established when the body, and therefore every part of it, is in equilibrium. So we shall isolate a small element of the body and derive the equation of equilibrium from its free body diagram. So I write that in general the state of stress the state of stress vary from point to point. The state of stress in a body varies from point to point. So our we have to determine the state of stress at every point or at any desired point in a body. So we analyze we analyze such kind of problems by dealing with the condition which is satisfied by the stress component when they vary from point to point. Okay, so these conditions will be established when the body and therefore every part of it is in equilibrium. So we isolate, we then we have we isolate a small element of the body and derive the equilibrium equations from its free body diagram from its free body diagram. Okay, so I have to draw the diagram at first. That is this is a cube. This is a cube. Now this is sigma x. This is sigma x plus delta sigma x. Okay, and this is sigma y. This is sigma y plus delta sigma y. This is sigma z, and this is sigma z plus delta sigma z. Now, and the other stress components are there. That is uh, tau xy, and this is tau yz. So this is tau xy, and this is tau xz, and this is tau yx. This is tau yx and tau yz. This is tau yx and tau yz, and similarly this is the shear stress, and this is also the shear stress, and this is also this is also the shear stress. So I mark the faces as 1, 2, then 3, 4, then 5, and then 6. Okay, so this is 1, this is 2, this is 3, this is 4, and this the backside plane is 5, and the front side plane is 6. So we now we put stress components in all 6 faces are following. Phase 1. In phase 1 we have sigma x, tau xy, tau xz. Phase 2 we have sigma x, del sigma x by del x into delta x, tau xy, del tau xy, del x, tau delta x, tau xz, tau xy, tau xy plus del tau xy, del x, delta x, and tau xz plus del tau xz by del x into delta x. In phase 3 we have that. I write it in the next page. So in phase 3 we have that sigma y, tau yx, tau yz. Phase 4 we have sigma y plus del sigma y, del y into delta y plus tau yx plus del tau yx, del y into delta y plus tau yz plus del tau yz, del y into delta y. In phase 5 we have sigma z, tau zx, and tau zy. So and phase 6 we have sigma z, del sigma z, del z, delta z, tau zx plus del tau zx, del z, delta z, tau zy plus del tau zy, del z, delta z. So why this term, that why this term is why we add this delta x, delta y, and delta z? Because the right hand face, the opposite faces, opposite faces is the x distance and this, sorry, the delta x distance and delta y distance and delta z distance away from the front face. Means in this case, in phase 2 we have, sorry, in phase 2 the stress components are delta x distance away from the phase 1. Similarly, in phase 4 the stress components are at delta y distance from the phase 3, and in phase 6 the stress components are at delta z distance away from the phase 5. So we have this delta y, delta z, and sorry, we have the additional delta x, means additional del sigma x, del x, mean this additional del operator we have, because the all faces in the opposite, I mean the all stress components in the opposite faces are as the delta term direction, means delta x, delta y, delta z respectively. The delta term directions, sorry, delta term distance away from the respective front face. So now let the body force components, let the body force components per unit volume in the x, y, sorry, x, y and z directions are gamma x, gamma y, gamma z. Gamma means the force, the body force per unit volume. So the gamma denotes the body force components per unit volume. Okay. So now for e sorry, for equilibrium in x direction, we get that sigma x plus del sigma x, del x, delta x, delta y, delta z. So we analyze the force component only. So this is the stress component and this is the respective normal area. So we see that this is if we take that this is delta x and this is delta z, and this sorry, I write it here that if we draw a coordinate, so this x direction is delta x, this y direction is delta y, and the z direction is delta z. So here the x direction is delta x, this is the z direction, in the length of the z direction cube is delta z, and the vertical direction length is delta y. So we see that this is, so what is force? Force is stress into area, or what is stress? Stress means the force perpendicular to the normal area. So we see that this is delta y, sorry, this is delta z, and if this is delta x. Okay, so this is the force means the stress per unit normal area. So we see that force is equal to stress into the perpendicular or the normal area. So this is stress, and the normal area means area of this phase means delta y into delta z. So I write that this is stress component into area. Here we resolve only the forces. So this is sigma x and minus sigma x delta y delta z plus tau yx plus del tau yx delta y delta z delta x minus tau yx. Look, in x direction we see this is sigma x plus del sigma x, and the y component of stress in h direction is tau yx, and the z component of the z component of stress in z direction is tau zx. So tau yx z into delta x. This is very simple, and the z component I write tau zx plus del tau zx del y, sorry, del z, del y, and this is del y, and this is here I multiply delta z. So delta x delta y minus tau zx delta x delta y plus, in the x direction the body force is gamma x into delta x into delta y into delta z. Y, this is the volume, delta x into delta y into delta z, and this gamma x means the body force component in h direction per unit volume. So this is force per unit volume into volume means this is also a force. So we resolve the force equilibrium in x direction, and we get that, and by simplifying it we get that, we see that sigma x yz, this term is also cancelled out, this term sigma, this term this term, and all the sigma x delta y delta z, sigma x delta y delta z cancel out. So this term and this term cancel out, this term and this term cancel out, this term and this term cancel out. So we see that we only get delta sigma x del sigma x del x into del x del y del z plus del tau yx del y delta y delta z delta x plus del tau zx del z delta z delta x delta y plus gamma x delta y delta z, that is equals to 0. Now we see that this delta x delta y delta z are common in this term, so we cancel this term, that we cancelled this all term, and we get del sigma x del x plus del tau yx del y plus del tau zx del z plus gamma x is equals to 0. Similarly, equating the forces, equating the forces in y and z direction respectively to 0, we get that del sigma y del y plus del tau xy del y, del tau xy del x plus y del tau zy del z plus gamma y that is equal to 0. This is in the y direction, and del sigma z del z plus del tau x z del x plus del tau x y x z y z del z del y plus gamma z that is equal to 0. This is in the z direction. So turning into the next page. So from equality of cross shares, equality of cross shares, we see that what tau xy that is equal to tau yx, tau xz that is equal to tau zx, tau zy that is equal to tau yz. Now, so the actually equation we get that del sigma x by del x plus del tau xy del y plus del tau xz del z plus gamma x that is equal to 0, that is in x direction, del sigma y del y plus del tau xy del x plus del tau yz del z plus gamma y is equal to 0 in y direction, del sigma z del z plus del tau xz del x plus del tau yz del y plus gamma z that is equal to 0 in z direction. So this equation, the above equations must be satisfied at all points throughout the volume of the body. Okay, so now this equation, this above equations must be satisfied at all points throughout the volume of the body. Now, if we want to establish the equilibrium equations for plane state of rest, then what will we get? So equilibrium equations for plane state. So if we want to establish the equations, means the equilibrium equations for plane state of rest, then what equations we'll get? We discussed in our previous class that for plane state of stress, as this is means that this state of stress is in the xy plane, so then sigma z that is equal to for plane state of stress we saw the z component of stresses, that is sigma z, tau zx, tau yz, or the and the body forces in z component, that is gamma z, the body force per unit volume. Actually, gamma is the body force per unit volume. So the stress component in z direction is 0 for plane state of stress. So we neglect this term. So for if there exists a plane state of stress in xy plane, then we saw that the z component of stress, that is sigma z, tau xz and tau yz, and also the body force per unit volume in the z component is equals to 0. So the above equation reduces to, so here we see the z component of the stress is 0. So the new equations for plane state of stress, we get that del sigma x del x plus del tau xy del y plus gamma x, plus del tau xz del z plus gamma x, that is 0, del sigma y del y plus del tau xy del x plus del tau yz del z plus gamma y, that is equal to 0. This component is also 0. And here del sigma z del z, this is 0, plus del tau xz del x, that is 0, plus del tau yz del y, that is also 0, plus gamma z, that is also 0 in 0. This is the stress component in x direction, this is the stress component in y direction, and this is the z stress components in the z direction. So we see that the z component stress direction are all are 0. So we get only the del sigma x del x plus del tau axy del y plus gamma x is equal to 0, and del sigma x by del y plus del tau xy del x plus gamma y is equals to 0. So this is the equation. This is the equations. This is the equations. This is the equations of for the plane state of stress, where the stress components as z direction is 0. Okay. So thank you. This is the end of this class. So today we learned about this. Sorry. Thank you.